Hey, what's up guys? This is Audie from ShastryNation, and today we're going to talk about diffusion and transport. Okay, so let's go ahead and write that. Diffusion and transport. Okay. So diffusion and transport relatively mean the same thing. Diffusion, they're just different words for different things. Transport means it uses ATP. We'll talk about more what each of these means. But there are really two main types of transport. So first, let's talk about passive transport. Passive transport is requires no ATP, and it's also called diffusion. And so, you'll have molecules, small molecules will be able to diffuse across the membrane and stuff like that. Mainly water. Water is a major thing that will diffuse across the membrane. This is actually called osmosis. Yeah, so this is actually called osmosis. And what actually happens is, in the cell membrane, there are little holes called aquaporins, and it literally means what it says: aqua, water pours in. It's pretty easy. Alright, so you have, let me draw out a little demonstration thingy. So we have a beaker here, and in green we have a cell. Okay, so let's go ahead and talk about three types of solutions. You have hypertonic solutions. Hypertonic, which is higher concentration. Now, keep in mind, this means concentration. Now keep in mind that hypertonic and whatever else I tell you is all relative to whatever it's being related to. So then you have isotonic, and you can tell by iso that it is the same concentration. Okay, and then you have hypotonic, which is lower concentration. Alright. So, for instance, let's say the cell is hypertonic. It has a higher concentration of water or something like that. It has a higher concentration of water. Well, in this instance, the water will, in fact, go out of the cell if it's hypertonic. Now, if the cell was hypotonic, or the water was hypertonic, then the cell water would seep into the cell. And for example, also if it was isotonic means same, and so there would not be a net movement. Net movement being that there is a certain direction that the water is being diffused into. In this instance, if both of these had equal concentrations, there would still diffusion and osmosis and all of that would still happen, but there would be no net movement. Alright, so let's, you might be like, oh, whoa, what's happening? Alright, but I will explain it to you. So if there's 40% of starch in this, and there's 100% H2O in the beaker, so this is the beaker, then okay, so if we take apart this this concentration of cells and stuff, starch actually cannot diffuse across the membrane like water can, and so we have to look at how much water is inside the cell. And so if there's 40% starch inside the cell, then we can conclude that there is 60% water. So we can write that down here. So 60% H2O. So we can conclude that, yeah, that there is 60% water. And so since there is 60% water inside the cell, and 100% outside the cell, water would go into the cell. They would go into the cell. The water from the beaker would go into the cell because water diffusion always happens from higher concentration. So higher. So from high concentration to low. Very important to remember in all of these problems that we're going to do. Okay. So there is actually a we have a couple of problems over here somewhere. Oh, there they are. Cool. Okay, so these problems are called water potential problems. So water So these are called water potential problems, and in these problems we'll just decide on, you know, what way the water is moving by comparing the water potential of each of the things we're trying to compare. So in this example, in the example we have right here, the cell would have a lower water potential than the water, and therefore the cell would have a lower water potential than the beaker, and therefore the water seeps into the cell. Okay. Let's go ahead and try this out. Okay, let's go ahead and try to solve this problem. Well, you might be like, whoa, what is this bars and this trident thing? You know, well, it's pretty easy. I can just give you a formula. It's right here. So you have the water potential, which is water potential is equal to the pressure potential plus the solute potential. And, you know, S for solute and P for pressure. So we can easily solve this one right here. So that would be, so if we looked at this, this one would be, let's see, actually, there would be 3 bars, right? So there would be 3 bars, and then you would add negative 4.5 bars. And you know, we don't have to convert this into anything else because these are in bars. You get the answer in bars, and this would be equal to what we're trying to find. So it's pretty easy. No algebra or anything involved. So you can just take this into your calculator and add them together. Now, I mean, you don't really need a calculator for this one. So it is negative 1.5. So the water potential in this case would be negative 1.5 bars. Sorry. Yeah. Okay. So then the other type of problems you'll have are solute potential problems. So we talked about water potential. Now, you know how here there is solute potential? Well, unless they give it to you, which most likely they won't give it to you, you'd have to find it for yourself. So there is a neat little formula for that too. So you have the solute potential. Ooh, I should write the. Okay. You have the solute potential, and that is equal to negative I CRT. So I, let me go ahead and write that in red. So I is equal to the ionization constant. And so what this really is for example, if you are, it's just how this diffusion and making solutions works. So for example, if you took sugar and you mixed it into a beaker of water, the sugar molecules or glucose molecules would stick together and they wouldn't be broken apart. But if you mix salt and salt being NaCl, salt will actually break apart and act as two different ions. They'll act as two different particles, basically. And so you have to take that into account. And so if you know if the substance will be broken apart when mixed in water, you can put down the amount of particles it will be broken down into. So for example, in the case of salt, if we had salt and we're trying to find the solute potential of salt, we would put -2, and or if we were finding in the other case, if we were finding the solute potential of sugar, we would put 1 because it wouldn't break apart. Right. Okay, so then we have C, which would be the pressure actually not the pressure constant, the molar concentration. So C for concentration. So it would be the molar concentration. R would be equal to the pressure constant, which is 0.831 bars. Or liters. It's like liters, bars, or liters per something. But you don't really need to know the exact thing. Okay, and then you have T, which is temperature in Kelvin. Remember that, and that would be plus 273. Yeah. Okay, so now we can go ahead and solve this. Okay, so you have so the question says a 15.15 molar solution of sucrose at atmospheric pressure at 25 degrees Celsius has an osmotic potential of -3.7 bars and a water potential of -3.1 bars equal to 1 atmosphere at sea level. So I guess this is trying to ask us which way this would transport into, I guess. So let's go ahead and look at what the thing is. So we have sucrose, so those aren't going to break down, so we know that we have to put 1. This is at 25 degrees Celsius, so we can put that there. And an osmotic potential is, and a water potential of -3.7 bars. So that would be -3.7 atmospheres. Okay, so let's go ahead and solve that. So we have, let's see, we would not break this apart, so you'd have -1 right here, and then you would multiply that by the 0.15 molar of that, and then you would have the pressure constant, so 0.831, and then you would have the temperature in Kelvin, which would be 25. Actually, I'm not sure about the. Let's just see. Okay, yeah. So yeah, it's 273. So it is 273 actually. You're right. Cool. So that would be 298 degrees. Sorry about that. 98. Okay. Okay, so we can go ahead and solve this out. So you'd have 1. You can just plug this into your calculator. So -1 times 0.15 times 0.831 times 298. Right. You would have so the solute potential. So yeah, solute potential would be -37.1457. So this question is weird. It's not really asking anything. So I guess we can just figure out what we have and what we don't have. So we have the solute potential. Oh, okay. So we're supposed to find the pressure potential. Yeah, we're supposed to find the pressure potential. Okay, so this is pretty easy. This is not too bad. Okay. Yeah, alright. So again, we have to plug this into that formula. So we would have water potential would be negative 3.7, and that's equal to the pressure potential plus negative 37.1457 from there. Okay, so then this is basic algebra. All we have to do is add 3.7 to both sides. Sorry, why would you do that? Okay, all you have to do is add, 37.1457 to both sides, and then you can find your answer. 37.1457. So this would cancel out. You would have negative 3.7, negative 3.7 plus, so you would get negative, no, you wouldn't get negative. Plugged it in wrong. Negative 3.7 plus 37.1457 would be 33.4457. So you'd get a pressure potential of 33.4457. Okay. I guess I didn't get the whole problem there, but you get the idea. It's pretty easy. You just have to plug it into the formula and things like that, and it's pretty easy. That's that. Okay, so you can also get other problems called YouTube problems, where they give you this YouTube. Oh, there's my very poor construction of the YouTube. And they have water levels here and here, or something like that. And these are pretty easy to solve. They just give you like different things and see if you can. It's just a matter of adding. So if we had like 25 of A and then like 30 of B, something like that, and here we had like 25 of A and 40 of B, and B was only B is able to go through is permeable to the membrane. So B, if only B is okay, so if only B is able to go through the membrane, this isn't too hard to figure out. But what happens is you just make up a chart. So you have side 1, you have side 2, and then you have A and then B. So what you do is if B is the only one that is permeable to the membrane, A is not. So if you have A is not permeable to the membrane, A would be the same. So it would be 25 and 25. No matter what, if this was 50, this would still be 50. If this is side 1, and this would be side 2. And then B in side 1, actually what you would do here is you would add up the numbers. So 30 plus 40, pretty easy math here, 70. And then you would divide that by 2, because if it is permeable to the membrane, you're going to have equal concentrations after it's been diffused across. So that would give you 35. So you'd have 35 on both sides. And those, that's basically all they'll ask you with these. Okay. So that is passive transport for you. That's all they can ask you for passive transport. That was a very weird question that I got. I don't know where I got that from, but I guess it was just asking me pressure potential. I don't know. Okay, so then you also have active transport. Active transport. So what is active transport? Well, active transport actually uses ATP, and this could be, think of this as pushing a ball up a hill. That obviously uses energy, and so this would go from low to high. So this would go from low to high, and this could be for, you know, things that the cell needs at the time, and we'll use ATP to grab and take into the cell. So it would be like, maybe there's a higher concentration of, you know, maybe it needs some food, and so it would take the food in. There's actually two different modes of getting stuff, and that would, the two different modes are, there are endocytosis. So there's endocytosis and then exocytosis. Endo and exo. Exocytosis. Endo is taking in, and then exo is pushing out. Okay, and then in endocytosis, there's phagocytosis. So phagocytosis, which is where, like, this would be something like an amoeba or something does. I think it's an amoeba. Yeah, but this would be something where a cell would engulf something, or like another animal, another organism or something like that, or food that it knows it's food. It'll engulf it and make a vesicle out of it, and it'll send in lysosomes or whatever to digest the food and use it as food. So phagocytosis is deliberate. It's done on purpose. And then there's pinocytosis. Pinocytosis is where a bacteria, for instance, can eat, just engulfs a certain area and hopes there's food in it. And if there is, it'll digest it. If not, whatever. So this is takes it in just because. And yeah, and so like transport is used to do many things, but here's some of the problems. You know, the things that we went over are some of the problems that you might get. This problem was a very weird problem. I don't know what it was asking, but it'll be a combination of both of these equations that I've given you, both of these formulas. Any problems they'll ask you will be a combination of both of these. And you might have to use both of these. You might do some YouTube problems like this. Ooh, I just went right over my work. Okay. You might use some YouTube problems like this, you know, but they're relatively easy. And one thing to remember is if the water potential is lower, it'll take in the water. I think I've mentioned that. But yeah. So much blank space. Alright, anyways, be sure to hit the like button if you liked it, dislike it if you disliked it. If you disliked it, please tell me why, so I'd like to know. And also, hit the subscribe button, because that would be cool. I'll see you guys in the next one.